All right, so hello everyone and welcome to our 11th Revolutionizing Healthcare session. My name is Nick Maxfield. I'll be moderating today's session and I handle the Schaar Lab's communications. I'm also joined, of course, by Mihaela who will be leading today's session. And I'm joined by Evgeny Saveliev, who is our lab's research engineer and a part-time PhD student with the lab. I'm also joined today by three of our clinical collaborators who will be giving presentations or taking part in the roundtable we'll be having in the latter half of the session. These are Vincent Gnanapragasam, George Mells, and Pierre Marquet, and I'll be introducing each of them individually in just a few minutes. But first, there's a sort of little disclaimer that I need to give about our lab's CPD credits for these sessions. So essentially, if you are a UK-based clinician, you can now claim CPD or continuing professional development credits under the Royal College of Physicians CPD scheme. That's at the rate of 1 credit per session for participating in these sessions, either by watching them live or by joining them or by watching them online once they've been recorded and uploaded. And in order to be able to give these, I need to make a short disclaimer to the effect that this is a non-commercial, no-fee event organized by our lab independently from our research sponsors. And we don't have any conflicts of interest, such as financial relationships, that would undermine the balance, objectivity, or scientific rigor of these sessions. We won't use these sessions to promote products or services, and any mention of our research sponsors will be strictly relevant to the academic content of the session, and will acknowledge sponsorship whenever such a mention is made. If you do want to know how to claim credits for attending these sessions, then I will just be giving that advice at the very end of the session, so please hold on until then. But first, I'd like to just give you a quick overview of what to expect from today's session. So our purpose with Revolutionizing Healthcare, as always, is to build a shared community and develop a common language between machine learning and clinicians. And to do this by defining and understanding medical problems through the use of formalisms and by mapping these to AI and machine learning solutions. And our previous session was kind of the first part of a double header around the broad theme of how to get machine learning power tools into the hands of clinicians. And to illustrate this, we showed a working demonstrator based on our own lab's Clairvoyance Pipeline Toolkit for time series. And within this, we showed some real-world case studies from the ICU setting in particular. And there was a focus basically on time series and individualized treatment effects in the time series setting, or which you could also call personalized therapeutics. And if you haven't seen that session, I definitely recommend taking a look at it on YouTube or on our website. Now, this time around, we're kind of completing this little double header and continuing with the broad agenda of getting machine learning power tools into the hands of clinicians. We will still be showing a demonstrator and showing real-world case studies, but it's a little different this time because these are related to dynamic time-to-event analysis and temporal phenotyping, which is a problem that we'll be framing in just a few minutes. And to break this session down for you time-wise, after my short introduction, Mihaela is going to give a brief presentation where she introduces themes for this session. And then we'll go into a presentation by Vincent Gnanapragasam on the theme of our session, which is temporal phenotyping and dynamic time-to-event analysis. And he'll be showing a new demonstrator and a tool that he co-developed with our lab and some case studies from that tool. And that's about 25 minutes in total. And then we'll have a short presentation by Evgeny, who will be giving a brief overview on our lab's approach to building robust machine learning tools for clinicians. And the latter half of this session will be given to a roundtable with clinicians, which is basically a structured discussion with the panelists we have joining us today. And if we do have time as well, we will have a Q&A session with our audience members. And about the Q&A session, if you do have any questions at any point in this session, either for Mihaela or for any of our panelists, please post them into the Zoom chat. Please do so that everyone can see them, so don't message a person individually with your question. And please feel free to share your questions at any point in the session. It doesn't just have to be during the roundtable. In fact, it would be better if you shared your questions during the presentations themselves, so we get a little bit of time to look at them and think about them. And we would like to limit our questions, if at all possible, to practicing clinicians, since you are our target audience. And also, just a quick reminder before I move on, if everyone could keep themselves on mute so we don't hear you throughout the session, that would be fantastic. Okay, and then we plan to wrap up the session after about an hour and a quarter, so at about 5:15 UK time. So next, I'd like to introduce our clinical collaborators and panelists for today's session. So first up, we have Vincent Gnanapragasam. And as I mentioned, Vincent co-developed the time to event analysis and temporal phenotyping tool that we'll be showing throughout this session. Vincent is a professor of urology at the University of Cambridge and an honorary consultant at Cambridge University Hospital's NHS Foundation Trust. And we're also joined by two other panelists, George Mells. George is an MRC clinical academic research partner in the Academic Department of Medical Genetics at the University of Cambridge. And we're joined by Pierre Marquet, who's head of the Pharmacology Toxicology Department at Limoges University Hospital and the team lead for the Pharmacology and Transplantation team at the University of Limoges and Ansel. So next up, we have a short presentation by Mihaela, as I mentioned. So she'll be introducing some of the broader themes of this session, such as our lab's approach to getting machine learning powered tools into the hands of clinicians and the topic of dynamic time to event analysis and temporal phenotyping. This will be given live. It's about 10 minutes in total. And again, if you do have any questions, please post them into the Zoom chat so that we can all see them. So Mihaela, if you're ready and you'd like to share your screen, please go ahead.
Wonderful. Thank you very much for the introduction. Thank you very much to everyone for joining us today and for making the time to interact with us and build this community. As Nick mentioned, today we are going to continue our series on how can we work together with you, the clinicians, to build these ML-powered tools in such a way that is useful for you. And as we mentioned last time, we really need to go through a four-step development. First, together with you, we need to understand the problem you are trying to solve, where you believe that machine learning could be useful and beneficial. In this conception stage, a lot of interactions will need to happen with you, the clinicians, such that we correctly understand the data and the problem at hand. Then we go back to the drawing board and we go through a step of modeling where we are formalizing the problem more rigorously and we are mapping it into solutions and algorithms. And then we develop these algorithms and validate them by implementing them, training them on the data that we have, and validating them on external data sets. In these two different steps, modeling and validation, we may have only limited interaction with you. But then the last stage is extremely important because at that stage, we have a model that hopefully indeed addresses the problem that we originally started with. And we now need to build demonstrators where we are reviewing together with you, debugging, testing, and evaluating the usefulness of the methods that we have built. And this is what we have done in the last last session on revolutionizing healthcare. And this is what we are going to discuss today. And this is the journey we have done together with Vincent. Both this session as well as the previous one relate to what I call bespoke medicine. If you recall earlier in the revolutionizing healthcare sessions, we discussed that patients are complex. They have different genetic background, environmental exposures, lifestyles, histories, and interventions. And this translates into different risks over time, variation in symptoms, health and disease trajectories, as well as responses to treatment. And we also said at the time that while personalized medicine fits the patient to a fixed pattern, at times based solely on a particular characteristic, for instance, genetic information, or the particular biomarker of this patient. In bespoke medicine, we recognize that the changes in patterns may evolve over time with age, with lifestyle, with onset of new diseases, with the progress of a treatment. So we need to adapt over time the patterns to which the patient is fitted. And the way to do that was through machine learning. And then what we can achieve in terms of bespoke medicine is identifying data-driven discovery of the interplay between multiple clinical factors and symptoms over time, quantifying more rigorously disease progression, inclusively the number of states the disease may progress on, the duration of the different states, which may also enable us to do early diagnosis. We can also identify causal pathways, evolution and coevolution of symptoms and morbidities, as well as temporal phenotyping and dynamic forecasting, as well as individualized treatment effects and side effects and interactions. In the last Revolutionizing Healthcare, we talked a lot about individualized treatment effects, counterfactual estimation, and personalized therapeutics. Today, we are going to talk about temporal phenotyping and dynamic forecasting. And if you like to review again what we identified as bespoke medicine, I invite you to take a look at a short write-up introducing this unifying framework for machine learning for healthcare, which includes a discussion of bespoke medicine. And this can be found on our lab website under Big Ideas, where we talk about building a machine learning framework for healthcare in a unified manner. Also, a discussion of bespoke medicine and the different methodologies and ideas behind it can be found in our second Revolutionizing Healthcare session. So you can see this session on our YouTube channel. Why bespoke medicine is important needs really no introduction. And really, today we are going to focus on cancer. And we are going to look especially at prostate cancer, but a variety of these ideas can be applied to other types of cancers as well as other diseases. And again, we are focusing on the idea of temporal phenotyping and longitudinal time to event analysis. This uses longitudinal time series data to build decision support systems for clinicians. And if you want to see the different machine learning methods that can be used for time series analysis, we invite you to take a look again on our website where we have clustered together a variety of machine learning methods for time series. In particular, time series is really a complex, multifaceted machine learning problem. And we highlight in this website different types of technologies that can potentially be useful. In the first part, we discuss how we can develop and tailor time series models for various healthcare challenges. And in another part of that piece, we discuss how to make them useful, for instance, by providing interpretability of time series models, uncertainty estimation, dealing with missing data, etc. But today I'm going to mainly focus on the first three topics associated with this. And one of the technologies that has empowered the demonstrator that we have co-developed together with Vincent and Evgeny is a technology that we call dynamic deep hit, which is looking at longitudinal survival data, which contains history of longitudinal measurements for a particular patient up to a certain time point, as well as time to event, so different types of events. And this data will be rightly censored, so right censored. So some patients may be lost to follow up. And also some of these events may be monitored in our data set. So for instance, in the data set that we have here, we may look at death from the primary disease, but we could have an entire set of events. For instance, related comorbidities, related side effects, recurrence, etc. So the models presented here could be easily extended to multiple events and multiple related events over time. And the goal is to estimate using machine learning on the basis of such data, the probability of a particular event happening over time. And for that, we often measure what we call a dynamic cumulative incidence function, which is looking at the probability that a particular event has happened, an event K has happened up to time tau. And this is on the basis of the longitudinal measurements accrued up to that particular time point. and also conditioned on the fact that the patient was alive up to that last measurement. Then the estimation of this incidence of the occurrence of a particular event takes other risks into account. So we can look not only at one particular risk or a particular event, K, but also at many other competing events. How are we learning? I'm not going to bother you with a lot of the details of the machine learning models, but let me just say that we learn complex representations using deep learning. But in order to really target them for different events of interest, we have what we call a multitask learning approach, where for every event of interest, for instance, a cardiovascular event, recurrence from a particular cancer, death from a particular cancer or related cancer, all these events have a particular cause-specific subnetwork that is learned specifically for that particular event. But the information that is fed on these cause-specific subnetworks is learned through a complex shared subnetwork, which learns across the different time series covariates. This is a deep learning model that we have used in this demonstrator, but we have also other methods, for instance, based on statistical methods, such as the work that I'm highlighting here, the Bayesian non-parametric dynamic survival model that is using Bayesian approaches based on survival models that are more statistics friendly. Then, as I mentioned, we are issuing predictions over time. So on the basis of whatever covariates we have that are accumulated over time, we are really looking at predicting a particular incidence of an event of interest or of a sequence of events of interest. Here are risks of developing, for instance, breast cancer death or cardiovascular disease death. So we look here at death for two particular diseases, and we monitor over time two particular biomarkers, antigen cancer and BMI. This is just for the sake of illustration. Then we don't only want to do time to event analysis on the basis of this longitudinal data, but we also want to understand whether clusters of patients are emerging over time. And the question we have asked ourselves was, how should we really group patients over time on the basis of this longitudinal time series observations? We have here 3 different patients, and the question is really which patients are going to evolve similarly over time. The conventional notion of clustering is looking at similarities in the time series observations, in the time series covariates. And this is going to group together, for instance, in this case, patient A and patient B, which have a similar evolution of these covariates over time. Unfortunately, though, this approach that I described before is not able to also lead to similar predictions of outcomes over time. So instead, we have developed a new notion of clustering, which we call an output-driven clustering or outcome-driven clustering, where the focus is not in the similarities of the biomarkers over time, but rather of the similarities in terms of future outcomes. So in this case, you can see that patient A and patient B are no longer clustered together, but rather patient A and patient C, because they are going to have a similar probabilities of experiencing the events of interest, for instance, death from a particular disease or recurrence, on the basis of the observations we have so far. So even though patient A and patient B are similar, there are sufficient variations between them that would make them lead to different outcomes over time, while patient A and patient C, even though they may look different, are actually going to experience similar events over time. How do we do that? We do that using machine learning method that we have developed in a sequence of previous papers, where again, the focus is of not learning similarities in the, let's say, in the covariates over time, like the traditional notion of phenotyping, but rather is using the outcomes to learn these similarities and what makes patient similar. This provides a new notion of phenotyping on the basis of which we can learn discrete representations of past observations that best describe these future events and outcomes. And this can be used, as you are going to see here, for decision support, but also it can be used for understanding of disease evolution and even planning and guidelines. For instance, if we know that certain patients are going to have similar outcomes in the future, this can be used for allocation of resources or personalized screening. Again, I went very fast over the ways in which we are solving these problems. If you are interested to listen more and hear more about the machine learning technology behind the demonstration today, I invite you to take a look at our research pillars dedicated to time series. Thank you.
Thank you very much, Mihaela. So next up, we have a presentation by Vincent Gnanapragasam. As I mentioned, Vincent is one of our lab's key clinical collaborators, and he co-developed along with our lab the tool that you'll be seeing basically throughout this session. His presentation is pre-recorded. It's about 25 minutes long, and he'll be framing the problem of dynamic time to event analysis and temporal phenotyping from a clinical perspective, as well as showing some patient case studies in our demonstrator.
Thank you very much for inviting me to speak in this session. I've always enjoyed listening to these sessions when I can, and very honored to be invited to talk today, and very honored to work with the Schaar Lab in this area. I'm Vincent Gnanapragasam. I'm a urology consultant at Edinburgh Hospital, and my specific area of interest is in prostate cancer. But rather unusually for what should be a surgeon, I'm actually more interested in managing early disease and how we can get away with not intervening. And that's the topic of my talk today, which is around prostate cancer, but particularly men with favorable risk disease on active surveillance, which is, I would consider to be the Cinderella of treatment options in prostate cancer. The first thing to say is that prostate cancer management has undergone a bit of a revolution over the last 10 years. And we already knew that many men diagnosed with prostate cancer don't come to any harm. And in fact, we've known this for many, many years. But trying to work out who these men were and what the actual consequence of non-treatment has only really crystallized in the last few years. Through studies like this, the large PROTECT study from the UK, which followed men after treatment or monitoring for 10 years and found very little difference in terms of outcomes, and in particular, no difference in terms of cancer-specific survival. Even in terms of progression to metastasis, the rates were actually very low in terms of the difference. What we do know is that many of these men are going to die of something else, and these are some elegant curves from a paper from Sweden many years ago now, which shows that in men with low risk and intermediate risk, which is the area which I shall talk a bit more about today, the risk of dying of either cardiovascular disease or other causes far outweighs that risk of dying of prostate cancer here in the orange. As a consequence, practice has changed, and for example, in my particular unit, the number of men on active surveillance has been progressively increasing year on year. And of course, it's very attractive because we're talking about managing prostate cancer without treatments which can cause significant side effects. But like I said, active surveillance is the Cinderella of prostate cancer management, and in fact, we know that people are doing very different things in many different places all over the world. This is just an example of a paper from some years ago showing all the different guidelines available and all the different methods of monitoring. And this is because no one really quite knows what to do about this, as men on prostate cancer are very heterogeneous, and so is the disease that they have. In terms of practice, this is even more stark. This is a paper we published again nearly 6 years ago now, where we did a simple survey of urologists around the region where we are to understand how they manage prostate cancer. And as you can see very briefly from these bar graphs, everyone had a different idea of what was safe to monitor and what wasn't safe to monitor, how to use to monitor, at what intervals, and what was the trigger for treatment. As you can imagine, for the patient, this is not a very satisfactory situation, and quite predictably, the rate of attrition, the number of men coming off surveillance, is actually very high, which really flies against the evidence you've already seen here about the fact that actually the risk of mortality is low. So why would someone come off surveillance over in that time when actually their risk hasn't changed? This paper showed that on average, after 3 years, about 40% of men would have come off surveillance. Now, this graph also tells you why they may have come surveillance, and it refers to things like progression, converting to treatment, watchful waiting, or other cause death. But this idea of progression is actually quite misleading, because you can't get two urologists to agree on what progression might mean, or you might get two to agree, but certainly not more than 3, 4, 5. They all have a different idea of what is risky. And this is because of a fundamental lack of understanding of what risk is in prostate cancer. But in terms of surveillance, it's quite clear that we are really at the very start of trying to understand how to monitor patients. And indeed, if you look at what NICE currently recommends, they have a very tight and rigid protocol, and there are 3 key things that they use: the PSA blood test, the use of imaging to keep an eye on things, and also perhaps repeat biopsies. And at the moment, the accepted guidelines suggest a very rigid standard protocol of doing the same thing all the time, regardless of the patient or the risk. But in Cambridge, we've been particularly keen to understand what is the natural history of disease that is untreated, because that's the only way you're able to do surveillance. And indeed, to do it properly, you need to know what is safe and unsafe disease, how to monitor, what is actually practical. For example, you can't see a patient every week and do a blood test every other week. But most importantly, you need to know when to stop. And this is a strange thing to say, but if you don't know what is required to stop surveillance, then you can't really build models or prediction algorithms. And finally, like in all of medicine, how do you make it personalized and safe? One of the key things that is hard for a clinician to understand is that we are watching cancers that grow, because that's what a cancer does. If it doesn't grow, it's not really a cancer. But it's the rate of that progression and whether or not it will spread and cause morbidity, which is the key to good surveillance. So the balance at what point you need to do treatment versus not is actually the key point. So in many ways, surveillance for a clinician is a much more risky thing to do than going in and treating everybody. But treatment carries side effects, which then the patient has to bear. So clearly, we should not be starting surveillance until we know what we need to do and how to do it. And if you're going to monitor someone, I've already mentioned we should be doing PSA blood tests regularly, interval MRI scans look at the prostate, but also biopsies, and also managing patients' expectations. How do you reassure someone that things are okay? How do you tell them if things are changing? When should you trigger a change to treatment? And really, this comes down to the heart of managing medicine in a modern era. It should be individualized, and everyone should not be having the same thing done. To start this process of understanding risk better and who should and should not be monitored, some work with it some years ago developed the Cambridge Prognostic Group System, which in effect is a 5-tier prognostic scoring system which outperforms the prevalent method, the NICE method. And what it shows is that actually the risks to an individual can be easily stratified into 5 groups, and in particular, these groups up here are the men that we'll be considering for surveillance. This model has a very high concordance index for prediction, and we've been able to transform that into clinically useful tools that we are using for our patient management. So much so that the UK National Prostate Cancer Audit is going to adopt our Cambridge prognostic system to report on the management of patients. On a more practical level, as it applies to surveillance, then what we have shown is that if you take men and you stratify them by either one of the top 3 categories, the Cambridge Prognostic Group categories 1 to 3, you can clearly identify that men in CPG1, which is the lowest risk, have an extremely low risk of prostate cancer mortality over a long period of time. And even men in the second category really barely benefit from treatment. It's when you get to the third category, the CPG3 men, that's when you start to see treatment differences and benefits. Now, on the face of it, this seems intuitive based on the models I've shown you, but what is really, really important is that because we can see these differences, we now know that if a cancer progresses from here, from this stage to this stage, then obviously treatment may be a little bit more beneficial, but overall, the benefits from treatment are actually pretty small. More importantly, when you get up to the CPG3 level, that's when it's clear that conservative management is actually the wrong thing to do, and you should come off treatment. So this work has suggested to us a model by which we know when surveillance should stop. Based on that, and based on our own fairly rudimentary algorithms, we've been able to work out a system to identify men at the highest risk of progression, and that is if they have a higher CPG risk of diagnosis. That's pretty intuitive. But another factor is something called the PSA density, and that's the PSA prostate blood test divided or corrected for by prostate volume. And that PSA density also turns out to be quite a strong predictor of progression to the CPG3 category. Using that, we've been developing a simple algorithm to help us in clinical management, and that has been found to be statistically significant. And we've been able to show that you can take men and put them into 3 categories at the moment. One where the CPG and PSA density are low. The second where you have either one attribute of a CPG of 2 or a PSA density which is higher, or the last category, which is the highest risk, where you have a combination of the two, and these men have a much higher risk of progression. In this particular study, we showed that the risk of progressing to CPG3 was 1%, 8%, and 22%. We were also able to show that in a separate cohort from Spain, suggesting that this has external validity as well. As a result, in Cambridge, we are actually using this to stratify our patients in the StratCans program to put men into different risk groups and design and tailor the surveillance and follow-up accordingly. And this in itself is already a major step. We are the first in the UK to be using such a stratified program, and this is currently the subject of audit and evaluation, but so far seems to be performing well. As a result of this work, we've devised a very simple crib sheet. Well, I say simple because in practice it is much simpler than it looks on paper, and we are rolling this out to the region to adopt as a way of standardizing how we survey patients. Clearly, there's a lot of detail in the practical rollout and steps, and that's not important for today. We've also encouraged patient self-management, for example, by using this online tracker we developed, which patients can use to track their PSAs. So the current state of affairs is that we can offer already a step change in current guidelines, which is grouped decision-making and risk-based follow-up. And this has helped us reduce the number of unnecessary follow-up visits, clinic resources use, and things of that nature. But this is a model that is based on data at the entry of surveillance. Yet we collect data continuously throughout active surveillance, and this is obviously a crucial aspect of how we are monitoring our patients. But once we get past that initial risk stratification and follow-up, then it becomes a little bit arbitrary as to what actually it means for someone who, say, has a change in their PSA, or the MRI shows a change, or perhaps the biopsy shows a bit more cancer or a different cancer. So our follow-up regime is fixed, and if something changes on that program, we try to adapt it, but it's not as intuitive as we would like it to be. So the next step, if you like, the next generation of this is to ask, how do you refine and personalize that care? How do you interpret and use the continuous data we're collecting every clinic visit to adapt and change that follow-up regime and actually give a prediction for when and if an event might happen and over what time frame? And really, this is the point at which we've been able to interact with the Schaar Lab, with Mihaela and Chang-Hee Lee and Evgeny and other colleagues to try and see whether we can use some of their highly innovative tools to help us in this management of patients who have not received treatment and in fact looking at a natural history model. The solution to that, or the potential solution to that, is a model which the Schaar Lab has developed called Dynamic Deep Hit Light, which is based on temporal phenotyping. In effect, this collects data over time and changes the risk predictions for the event of interest, which for us is the CPG3 event, and allows us to adapt the follow-up to that. This is a schematic of how it might work. You have a patient who is diagnosed and has baseline covariates, and through their follow-up and through that process of PSAs, MRIs, and biopsies. Now, throughout surveillance, you get additional data being collected, again, around these 3 key attributes. And for each visit, these can be put into the model to estimate the survival, or in this case, progression risks over time. And from that, you can work out the evaluation time to an event or not. And you can use this to adapt your follow-up in terms of how often you might see them, when the next set of results might be, and whether a particular result has changed at endpoint. And that is what we've been working together with some exciting preliminary data. This is a study which we are currently performing, and I won't go into the details, but We have a very highly annotated cohort in Cambridge with data attributes that we can put into such a model, including ethnicity, family history, their risk assignments, the Cambridge prognostic groups, the MRI stage, and also the type of MRI signal they had, or Likert score. Over time, using the temporal covariates, we can look at the serial PSA values, the serial MRI, and also rebiopsy attributes as well. If you plot our cohort over time, you can see that the number of men progressing to CBT3 does actually accumulate over time, as you would expect it to do, because this is cancers which can progress, but certainly not by all means. And if you even look at the median follow-up at 5 years, the vast majority of men are still on surveillance. Now, in summary, the analysis of our data, comparing it to baseline models or landmarking Cox, which is the other type of analysis you can do with data such as this, shows that a dynamic deep hit light model outperforms these. And really crucially, it does even better with the more data you can collect and the longer follow-up you can do. So clearly at baseline, if you simply use those data, then the models are pretty similar. But over time, the baseline models tend to perform poorer. And this is where models like the DDHL model actually show their strength and value. Even more exciting is the fact that the model can learn from different behavior patterns and actually put patients into clusters or groups. So almost approaching it from the other way, where you collect the data in a continuous and non-selected way, but actually start to put them into clusters of behavior. The key thing is that a patient does not stay in a cluster, but can move between those clusters depending on the risk attributes and the observations over time. And these is a very nice illustration how those clusters can actually stratify those patients and actually tell you about the risks of progression over time. This is an illustration of an example of how that might work. The yellow star representing a patient with a particular set of PSA and PSA density attributes for a given grade and stage of disease. And if you change that grade and stage or the PSA and PSA density, you can see how that risk will change between the clusters as you go through that process. Again, as I mentioned, if you take the cohort as a whole and you look at the risk of movement between clusters, you can actually map this out for an individual and indeed for a group. And you can see how the risk of moving, say, from the lowest risk cluster to the highest risk cluster, or indeed with an observation pushing them back into the original cluster may work. And the model is dynamic depending on the observations that you do. So this project, to me, illustrates the power of the machine learning models that the Schaar Lab are able to do. And it's highly exciting for actually creating a tool which I can use in the clinic for predicting risk based on the current situation, the historic performance or pattern, shall we say, and indeed new attributes and new data that comes in. This then allows me to personalize the follow-up regime for that person and do away with either static follow-up regimes or indeed dynamic or indeed baseline ones which are inflexible. What we'll do next is we'll look to see how the demonstrator developed at the Schaar Lab is actually able to be used in a clinic interface in a mock-up setting to see how a patient can move on. So let's see how this might work in practice using the DDHL model with an illustration of the demonstrator which has been expertly put together by Evgeny. So this is a patient I might see in my clinic. He's a gentleman of 57. He's a white gentleman with no family history. He's got an MRI Parvard score of 2, which effectively means that there's not much of a lesion there. He's a grade group 1 or histological group 1 at entry and a CPG 1, so this puts him into the lowest risk bracket. And his PSA is only 3.46. So this is the kind of chap we expect to do quite well. And indeed, we know he did quite well for this demonstration purposes, because if you look at his historic risk over time, you can see that really not much of the events happened, which is what you'd expect. And in terms of his cluster assignments, he's actually progressively gone down the different clusters of risk, as explained earlier on. And we can see this best in this illustration here, looking at the cluster space, where over time and closer to the observations we have to current date, you can see his risk has actually moved further and further into the most favorable clusters. Now, in terms of this chap, then we know that his interval follow-up can be quite long. The risks of him actually developing a problem are also quite low. So the question really is what happens in terms of modifying this. Let's say we have a real-time patient who has been doing so well, but something changes. So we can look to see how this might happen if we go to a new observation tab on the demonstrator here, maybe push back his history to an earlier time point and start to look at changing the attributes to see what happens. So I'm going to go back to quite close to where he started his surveillance, and we can see how that works. So clearly at that time point, he had a very small risk of progression, but let's just imagine that we change his attributes, for example, and let's move his PSA up to a level of, say, 8 or something like that. But let's say he had an MRI which showed that something had changed. His MRI stage has gone from a T1 to T2. And in terms of that change in the precise score, meaning to say that the MRI looks a bit different, we have another biopsy done. And of, say, 12 samples that he has taken, we actually have 3 which are positive. And you can see that as we move the cursors and the buttons, his risk over time is predicted to increase. And this is what you would expect. The more biopsy scores you have positive on new observation, the higher the chance you will progress. The MRI changes that also suggest that things may progress as well. And this is even more stark if you were to change his grade group, which was a 1 before, and we move him up to a 2. And here you can see that the previously flat trajectory actually now suggests that we should follow this guy up more closely because it looks as though an event may happen in the future. Now, we know it didn't happen, but let's imagine this chap was in the clinic and had a new set of observations. It clearly changes the paradigm for him in terms of surveillance. In that context, then, a model like this means that rather than just putting him into the fixed regime based on his previous set of data, which would have suggested we could have seen him for long intervals, we might see him sooner. Now, of course, if we change these attributes and let's just say this time his PSA was actually pretty much where it has been before, around those levels of about 5 on his repeat observation, we'll take it down to that. And let's say he had an MRI score which showed no change, which is called a precise 3, and also no change in his stage. And certainly because of that, he didn't need to have a biopsy done. His histological grade group changes back to what it was at the beginning. And you can see his trajectory was what actually happened in real time. So this is a nice illustration of how we can use this model to change our track in terms of what we're doing with this gentleman if the circumstances changes. And here we have another case to show the demonstrator's use in an altogether different type of individual. Now, this gentleman is 66. He's also of white descent or Caucasian descent, no family history. He has got a lesion on his prostate of an M3 score, but he's also at a higher risk because he comes in at a grade group 1, but his PSA is high, so he falls into the CPG2 bracket. Now, these gentlemen we know can do very well on surveillance, but there is a slightly higher risk compared to the case we saw before. And you can see that his PSA over time has shown a trend to rise, particularly up to the higher levels, which puts him into the CPG3 category. And if we look at his historic profile over time, you can see that he actually did have the event, which occurred some 3 years, some time, after starting surveillance. So over that period of time and between each observation, his risk of an event happening actually was higher than the other gentlemen's. But each time he had an observation which reset his trajectory, that allowed us to carry on with surveillance. But eventually, he did actually develop those events. And that is what we would expect to see in somebody who has that higher risk. But of course, not everyone gets those events. And when those events happen, can be difficult to be certain of. In terms of his cluster or risk, you can see that he remained in the cluster 4, highest risk, throughout really his surveillance journey. And this is illustrated in the cluster space, where over time he didn't really skew to the lower risk groups or clusters, but remained actually in that cluster, though perhaps on the more favorable side of that behavior pattern. So If we were to take this gentleman, say, and go back again, like we did for the other case, to an earlier time point, let's say taking it towards the earliest point of his surveillance, then his observations up to the point of this new set tells us that actually he already has a baseline risk of progression. And if we were to enter attributes which were pretty similar to where he started, let's say he had a PSA which was coming in around 10. Let's say his MRI did not show a change. His MRI stage remained the same and prostate volume was the same, and we don't have any new characteristics. Then his predicted risk of developing an event was not overly high, but significantly higher than the other situation. Now, in this gentleman's case, let's just say we change his attributes again. Let's put his PSA up higher, getting up towards the levels we see towards the latter part of the journey. And let's say again that he had an MRI precise score, which means that something had changed. And let's say this time his biopsy co-involvement was positive, and in particular, I was heading towards an all-cause positive situation. And you can see immediately that his risks becomes higher and the probability of events becomes very real indeed. If you then add in his risk increase with changing his grade, you can see that he's got an almost 80% risk of progressing to the event over a time horizon of about 1,900 days. So this kind of chap, where the history tells us of his baseline risk being higher, means that every observation has that added increased risk if they are higher than the ones before. If they remain in status quo, then he can actually carry on as he is. This allows us then to look at this chap like this and say that based on the current set of characteristics, we may want to be talking about treatment perhaps because his probability of events is quite high, or indeed saying to him, look, we need to make sure that we're keeping a close eye and we can tailor the follow-up and make it much more frequent in this particular case so that we can pick up those events at a time when we can do something about it. And this is the kind of thing you would see that actually as the probabilities accumulate, his interval between observations also starts to get much more closer, and that's what we did instinctively as clinicians. But a model like this allows us to do this in a much more intelligent way and adaptive way.
Okay, so our final short presentation is by Evgeny Saveliev, our lab's research engineer, and it's just about 3 minutes. It's a high-level look at our lab's approach to developing practical, robust machine learning tools for healthcare.
Hello, everyone. My name is Evgeny, and I'm the research engineer at the Schaar Lab behind the Clairvoyance project. I will discuss clairvoyance as a tool for practical and robust machine learning time series in healthcare. Getting advanced machine learning and AI algorithms to the stage of being used in practice has some unaddressed challenges. How can we get from a scientific paper to a useful tool actually used in a hospital? In the world of academia, there's a vast and ever-growing range of publications introducing the most cutting-edge and the most sophisticated machine learning algorithms. These are, however, often narrow in their application and have been tested on a small number of classical datasets. There is no guarantee that an algorithm that has narrowly beaten some benchmark score will actually perform well in real life. In order to develop robust, practical, and useful machine learning tools, we must prototype such algorithms. In other words, we need to create tools that give the community of clinical professionals the ability to see, try out, and actually play with what such models can achieve. The models should be applied in new settings and tested on multiple new data sets. The practical usefulness for the clinicians and their patients then quickly becomes apparent, and the academic community can gather feedback and refine the algorithms and tools that it can deliver. Often, novel problems and questions previously not apparent can actually emerge from such interactions. To our knowledge, Clairvoyance is the first such collaborative effort led by an academic team. We developed a framework that is able to handle complex methods for complex problems. We have demonstrated this today in the context of time series, time to event analysis, and temporal phenotyping. Clairvoyance then presents the problem to the user in a visual and interactive way, which facilitates the evaluation and refinement cycle. In fact, I have been developing clairvoyance with the following points in mind: the ease of prototyping new algorithms from the perspective of researchers, a flexible and easy to adapt and improve visual interface, the framework that ties together multiple healthcare problem settings and data sets. Beyond treatment effects demonstrated today, clairvoyance has many other problem settings in active development, such as patient clustering, time series forecasting, and survival analysis. And so in closing, here you can see the URLs to actually try out the clairvoyance code base. Thank you.
Okay, so now it's time for our clinician roundtable, and I've already introduced our three clinician panelists, Vincent, George, and Pierre. So I think we can pretty much just dive into it. So we actually have a few questions already lined up, and I think what Mihaela is going to do is basically take each question and throw it to one or more of our panelists. So Mihaela, if you want to go ahead and ask the first question or the first discussion topic.
Yes, so I would like to ask George and Pierre, how do they think that phenotyping is currently done, and how do you use such tools in clinical practice? You saw a little bit of what Vincent said about prostate cancer, but I was wondering in other settings, such as the ones you are looking at, how do you think about this?
I'll dive in first, actually, Mihaela. So, I mean, I'm a hepatologist by practice. And we have fairly standard approaches to risk phenotyping. I think we're mainly talking about risk phenotyping here in hepatology. So we can learn a lot from blood tests, standard blood tests, liver tests, kidney tests, full blood count plotting, from scans, such as ultrasound scans, sometimes MRI scans, certainly from elastography, which is a non-invasive means of measuring fibrosis. And we learn quite a lot from biopsies. And we either interpret those in isolation or in many branches of hepatology, we have developed various risk stratifying thresholds, or indeed multivariable clinical prediction models, which are not dissimilar to what has just been described, but do differ in one critical aspect, I think, which is that they tend to be based on a static set of measurements, a snapshot in time, and they don't take time series into account. They don't do the dynamic forecasting, which you mentioned previously, and I think that is the critical difference, actually, certainly in hepatology, but I think probably in medicine in general.
And Mihaela, I'm personally involved in transplantation, organ transplantation at large, be it kidney, liver, etc. And we have exactly the same paradigm as George just mentioned. We have a functional test, we have lesions that we can see on the biopsies, we have biomarkers for such lesions as well. And now we tend to have scores to predict more or less graft survival or patient survival. But the difficulty is how to offer the scores to the clinicians in an easy way to put their hands on it and also to interpret the results, and how to use these scores to change the patient surveillance or patient follow-up. And this is not granted, and there is still a long way to go.
Thank you very much. Nick, maybe I can go to the next question. So my next question is whether are the temporal phenotyping tools presented that we have co-developed with Vincent useful for your own setting to serve the patient in front of you? And in what scenarios do you envision using such a tool as decision support? And also maybe more generally extrapolating from your own knowledge to maybe other diseases and patients, when would such a tool be more useful?
Again, if I can just dive in there. So I think the first question, I mean, strictly speaking, I guess one would have to develop the platform, validate the platform, and then test it in practice to know whether it does serve the patient better. So I guess you would have to go through that whole derivation validation process. But intuitively, I think that models that take temporal trends into account must surely be better. So if we just take some examples in clinical hepatology, one of the key measures that we use is the bilirubin, the serum bilirubin. That's an excellent marker of liver function. And in liver diseases, if the bilirubin is elevated, we tend to be slightly concerned. If the bilirubin is elevated and it is rising, then we're much more concerned. And if the bilirubin is elevated but it is falling, then in general we're much less concerned. And I think many of the models that we currently use don't really take the information that intuitively that we know from those trends into account. Similarly, models that are based on a snapshot in time won't really take into account the fact that the risk will often depend on the duration of active disease. So in hepatology, for example, if a patient has autoimmune hepatitis and the autoimmune hepatitis is uncontrolled for a long period of time, a risk prediction based on one snapshot may underestimate the true risk to the patient because, of course, they've had many years of uncontrolled disease and are actually slowly but surely developing liver fibrosis. And along those lines, similarly, the coefficient of any given covariable might be different according to the stage of disease. So an elevated bilirubin in somebody who does not have cirrhosis, for example, might be quite different to the implications of an elevated bilirubin in somebody who does have cirrhosis. And so on and so forth. So I think intuitively, my answer must be that models, dynamic forecasting, must surely predict outcomes better than models that are based on snapshots in time. But as I say, I think you would really have to test the model in order to know that for sure.
In my field, Mihaela, I believe that also it would be important for patients where the treatment can be adapted, where you have several options depending on the severity or the evolution over time, and that sometimes it's difficult to figure out which treatment to use first and then when to switch to another, etc. So triggers to help clinicians to figure out when they should change treatment, not waiting for obvious failure or obvious adverse effects, for instance, would be very useful. And in transplantation, we also have systematic biopsies because we know that graft rejection becomes apparent too late generally. And so clinicians want to know as soon as possible when something's wrong in the graft. So they do biopsies that most of the time are normal. But it's invasive, it's uncomfortable, it's costly. And so if we had a way of avoiding such systematic biopsies and waiting for a signal to trigger a biopsy when it's more probable to be productive, that would be a bonus.
Mihaela, you had a couple of other questions actually, which were things, in what scenarios would we envisage using dynamic forecasting? I have to admit, when I thought about that, I couldn't actually think of any conditions where dynamic forecasting wouldn't potentially be applicable. But just for the sake of argument, I did, when thinking about this, I came up with a few criteria that we might employ. And Pierre, your thoughts on it would be, of course, invaluable, but perhaps conditions that have serious outcomes, I thought, as being a baseline criterion. The condition, I thought, should at least have interim serial measurements where we would expect those serial measurements to have some kind of prognostic ability. And of course, the accurate prognostication, just as Pierre was saying, the accurate prognostication should influence the management in some way. Either the frequency of management of monitoring or the choice of monitoring, or it should influence the decision to treat the patient or the choice of treatment that might be offered. And provided those criteria were fulfilled, then I think actually dynamic forecasting would have a role. But I couldn't, as I say, I couldn't really think of any conditions where it wouldn't potentially have a role, except perhaps for hemorrhage and critical ischemia.
So maybe that allows me to ask a question to all of you, George, Pierre, and Vincent. All these tools, of course, may be helpful in practice, but in order to turn them into actionable, useful decision support systems, one would need to, I assume, validate and run maybe some form of trial to show the fact that we could use them to either increase the number of observations or decrease the number of observations. How do you envision taking such tools into practice? And maybe I can start with you, Vincent, and go to Pierre and George. How do you feel that we could take these tools now to real practice? What do you think will be the next steps and challenges associated with it?
So that's a question with perhaps a multifaceted answer, because actually there are multiple tools, as has been indicated by my colleagues here, which have already been developed. And actually, you find that clinicians will use different tools depending on their own experience, their own beliefs, and things like that. And a lot depends on how much validity a tool has, how well it's been tested, how well it's been proven. And even then, there is a challenge in getting clinicians to actually accept and use tools. It is almost inherently built in clinicians, particularly consultants, that they know what to do in a way. And we have actually done work, as I have mentioned to you before, Mihaela, on other tools we've developed to understand actually how much clinicians do know in my own area, for example, in predicting prostate cancer mortality. And it's quite frightening how way out sometimes the predictions are, but they're using their own intuition. So it's not as simple as developing a really good tool and even getting a guideline to say this is a good tool. Work has to be done to actually demonstrate it. It takes time to embed. You need to show the evidence. And it's actually a fairly slow process. And the evidence for this is clear. You can see that so many organizations provide tools, and it's unlikely that a disease type has got only one tool which is used consistently. So I think that it's not just the development of the tool, although that's something you have to do, but on a large scale. You also have to educate and actually teach and change the paradigm a bit, because in a way, what you're asking is clinicians to say that the tool will tell you rather than what you think may happen.
Mihaela, as a clinical pharmacologist, I would say you have to provide clinical evidence. So you would have to compare patients with or without your tools and see whether the first do better. But when you delve a little bit deeper into that, you realize that the tool does not propose treatment. The tool does not propose action. The tools proposes a prognostic, and then the physicians are free to react based on this prognostic. So I believe that another way of doing that is to exploring blindly existing databases and comparing different tools to clinical experience. The same database could be provided to clinicians, and they could make their own guesses about patients' outcome and the way they would deal with them, as compared to, I would call that a formalized physician experience, because a prognostic tool is more or less a formalized way of using the clinical data that the physicians already have. It does not rely on new kinds of data. And you could make a kind of competition and look at who is doing better in the end, prognosing and not treating, obviously, because the treatment will stay in the hands of the clinicians, obviously.
Yeah, yeah. I'm not sure I've got much to add to those comments, actually, but along the same lines. It is, of course, possible to see whether certain key metrics change after the introduction of a dynamic forecasting tool, for example, and whether those metrics revert once the dynamic forecasting tool is no longer used. I see amongst the audience is Dr. Jimson, who developed a system called a transplant benefit score, which we use in liver transplantation to allocate the liver transplant, the graft, to the best recipient based on their likelihood of benefiting from that transplant. And the way that has been the use of that approach, and Dr. Jimson should be unmuted to correct me in case I'm getting this wrong, but the way that we've chosen in hepatology to test this platform is to compare the survival of patients on the waiting list and survival of recipients and so on before and after this platform is employed. And that's a sort of epidemiological method which can be used to test certain platforms. That approach would be highly applicable, for example, to this the system used for surveillance of prostate cancer. When you're dealing with a much rarer disease, of course, it becomes more complicated. But in common conditions, common important conditions, and those are the conditions where you'll be developing these models in the first instance, then that essentially epidemiological approach should be possible.
I guess we shouldn't unmute Alex. We should discuss this in an entire new session next time, I would propose, because I think it leads to much more complex discussions, and maybe we should take them as a separate session, I would propose.
Absolutely. He can tell me if I've got it wrong separately. So
Shall we got a question, I think?
We do indeed, from Ern, and it may be one question, it may be a two-parter, but Ern, we were wondering if you wouldn't mind unmuting to ask.
Yeah, absolutely. Thanks a million. Great discussion as always. I thought I'd ask the second one, which I think is possibly the more interesting one first, if that's all right. Basically, when you're forming prediction, dynamic prediction or any other kind, you can only base that upon what you measure. So there may be unmeasured features that could be very informative. We just don't know that we should be measuring them. And I was wondering that if we had enough data, do you think it would be feasible to, for example, subsample or include features beyond those that we currently build a predictor on the basis of, to try and find out new things and discover new features that might support and improve our prediction?
So thank you, and definitely. So currently in the model, we use whatever data we have, but of course we didn't show this view, but together with Vincent and Evgeny, we identify what features are important and what features are important over time. So that view already exists, but what you are proposing seems to go one step further, which is what we often call in machine learning active sensing. So trying to identify when next to measure what feature and for what individual. And this is something that exists as a methodology, but we do not have that in a demonstrator. So maybe that is something to take forward with the ones among you that are interested, to try to really identify what type of tests should be made next, when, and for whom. So again, methodology exists, but not in this demonstrator, but we do have a feature importance. I don't know, Vincent, if you want to say anything else.
No, I agree, Mihaela, and you're absolutely correct that obviously what we have to build the model is what we use to monitor, to diagnose and to monitor. But one other thing which occurred to me is, and again, this comes down to the whole concept of why you survey cancer rather than treat it, is because it's the balance between mortalities and risks and competing risks. And where that's really important is overall mortalities. It's not much use to only know when someone progresses. There's no point if he's 85 to be thinking about treating someone when he's got all kinds of other conditions. So actually, the power in the tool that we've been developing is, this is just the first iteration, actually a model which incorporates competing risks, other competing mortality, and balances that against the progression of the cancer itself, is where will be superb. And that's exactly where I think your point comes in, because then you bring in lots of things, even blood sugar levels, hypertension, BP, all sorts of other things start to produce a composite mortality risk, shall we say, which is something which I've been thinking about for some time, which in my own field is actually probably the most important thing, because it's a disease of the elderly male. And we clinicians, surgeons just look at the cancer mortality. They don't think about the other mortality.
Lots of food for thought and additional work to do.
Okay, so is that, I just wanted to check that none of our other panelists wanted to weigh in on that as well. And if not, I think we'll just go to our wrap up then. Okay, so I think that's pretty much all we have time for this session, since it's now coming up on 1:15. And thank you to everyone for joining us. I would just like to talk very briefly about what you can expect from our next Revolutionizing Healthcare session, which will be on November 30th. And our topic for that session will be organ transplantation. So please join us then for that. And of course, I will share updates about this session via our mailing list within the coming weeks. Also, today's session will be, as always, uploaded to YouTube after a little bit of editing. Please expect that just in a few days, so by the end of this week. I also thought I'd just mention that we do have a little bit of relatively new content on our own lab's website. This is sort of a page dedicated to the impact of our lab's research. So whether this is within specific areas of clinical impact, or, for example, the way we partner with clinicians, or on policy impact, there's a range of different areas where our lab has impact, and these are kind of outlined on that page. Now, another point is, as I mentioned, we can offer CPD credits for those of you attending these sessions or even watching them online. All you really need to do is just email me, letting me know which sessions you've watched, and basically whether you watch them live or whether you watch them on YouTube. And then I will send you a CPD certificate, which will allow you to apply for credits via the Royal College of Physicians CPD site. I think I also just noticed in the chat, someone asked for a YouTube link for this session. Basically what happens is I need to just edit the session and then I need to upload it to YouTube. So you'll get that by email in a few days' time. And a quick other request from me, if you do have any clinician friends or colleagues who you think might be interested in joining these sessions, please do let them know by sending them the URL that you can see on this slide and asking them to sign up. Obviously, building a community is the main reason we're doing this, so word of mouth is extremely important to us in that regard. And I guess before I go, I would very much like to thank, in particular, our clinician panelists and Vincent, both for his presentation and for taking part in the roundtable, and also George and Pierre as well. And thank you all very, very much for joining. I do look forward to seeing you on November 30th for our session on organ transplantation. In the meantime, please take care and stay safe. Thanks so much.